Hi. Gosh, sorry if I just blew out your ears. Anyway, it's great to be at Devox France. This is my first time at this conference, although I've been to the Belgian version many times. It's nice to see all of you. Thank you for coming. And today I'm going to be talking about effective Java because I finally got the third edition out. I guess it's been a long time coming. Thank you. It's got one new chapter, 14 new items. 2 of the old items have been sent off to a retirement home. And all of the existing items have been thoroughly revised, especially the code samples. Pretty much everything in the book has been given a spring cleaning. It needs that every 10 years. A brief history of the book. The first edition came out in 2001, which is kind of amazing, right? I mean, 2001, you know, many of you were like little school children back then. Back then, it covered the Java language itself. It was only 232 pages long. The second edition came out because primarily of Java 5 and Java 6, and so it covered generics and auto-boxing and for each and varargs and stuff like that. And it lasted a good 8 years. And then in 2017, at the very, very end of the year, I published this edition, and it covers all of the Java 7, 8, and 9 features, primarily lambdas, streams, optionals, and so forth. I set out to write a really small book when I wrote the thing in 2001. It was an homage to Scott Meyer's Effective C++, and I really liked how much information he packed into a nice small book. And I kind of succeeded. I was aiming for 200 pages. I came in at 232. But here's the thing. It's hard to write a small book about a large language, and Java has been growing and growing and growing. So has my book. You know, it's now 366 pages of main text, and you know, I forget what, 420 pages of book. Oh well. Of course, I cannot cover all the new material in even a 1-hour talk, and this is a 45-minute talk. So I'm going to concentrate on the lambdas and streams chapter. I've got 5 topics to cover. If I can do it in 45 minutes, that's great. And if not, I'm going to skip the last section. Question, by the way, timekeepers, the clock is not counting down. Can you make it count, please? Thank you. All right. That means I get a free extra minute, though, so I guess that's a good thing, right? All right. So first topic that I'm going to cover is that you should prefer lambdas to anonymous classes. And it's pretty straightforward. Historically, this is how you did a function object in Java. It was kind of ugly. Here, I'm sorting a collection of strings, which I call words. And in order to do that, I create a new comparator of strings, you know, which I do by overriding its int method and saying, hey, I want to return integer.compare of the first string's length to the second string length. So basically, this sorts the strings in order of length. That's great. And it was adequate for classic object-oriented design patterns like the strategy pattern and the command pattern, but not so good for more modern functional programming idioms, which have become popular of late, and that's why they added lambdas. And using lambdas, it's much, much prettier. Here's the same thing. Collections.sort of words, but instead of that big, ugly, anonymous instance creation expression, we just say, hey, a lambda that takes 2 parameters, string 1 and string 2, and returns integer.compare of the length of string 1 and the length of string 2. So that's a lot nicer, right? But you can do even better, it turns out, because they added to comparators the comparator construction methods. And here I've statically imported comparing int. So I can just say sort the words, comparing the ints that are the string lengths. So that is a comparator construction method containing a method reference. I'm going to be talking about method references in the next section. And you might think that that's good enough, but in fact you can do even better because the designers were nice enough to add a sort method to the list interface using default methods. So you can just say words.sort, comparing the ints that are lengths of the string. And I think you can't do too much better than that. That pretty much reads like prose. So how does all this magic actually work? And the short answer is type inference. You know, when I do this nice little lambda, what it's really saying is make me a new comparator of string, and the 2 arguments are of type string, blah, blah, blah. How does the language know what these types are? And the answer is it infers them. But how does it infer them? Well, there's an entire chapter of the Java language specification all about type inference. How many of you have read and understand that whole chapter? Be honest. Yeah, so there are about 3 of you, and I'll bet you guys are compiler engineers, language designers. You know, those are the only people who really care about this, or PhDs, because really they want to spend as much time as possible just like doing stuff. Ask me how I know. Anyway, so the idea is that most people have no idea how type inference works, and it's okay. Treat it as magic. Just leave out all the types unless either they make the program clearer. Sometimes it's clearer if you actually tell the reader of the program, this is a string. And you might think this one is a string, but it isn't. It's actually a character sequence or whatever. Fine, go ahead and specify them explicitly if they make your program clearer. And other than that, if the compiler needs more types specified, it'll tell you. So only add more types if the compiler demands them. And a caveat regarding type inference. It relies on generic type information. So if you don't provide that information, it simply can't work. In the case of our little sample program, it only worked because I declared words to be a list of string. If I had used the raw type list, it simply wouldn't have worked. So the second edition of the book said, hey, don't use raw types because they make your code uglier, it's filled with casts, and they cause needless runtime bugs. These bugs could have been caught at compile time, but if you don't specify the type information, the compiler can't catch it. Well, that advice has been made much stronger in the third edition because of the fact that the penalty now includes that you just can't use lambdas if you don't specify the generic type information. So it's really mandatory to use generics now. You can't use lambdas if you don't use generics. Now, I'm going to show you a piece of code that was in the previous edition of my book. You might recognize it. I was actually pretty proud of the code at the time. It's an enum with constant-specific class bodies. So we have a little enum called operation that has constants for plus, minus, times, and divided by. And each one of these things knows how to do its operation. And the way I've done that is I have an abstract method on the enum called apply, takes 2 doubles and returns a double. And then each of the enum constants overrides the double method and performs the right application. So plus adds them, subtracts, minus subtracts them, and so forth. Makes sense, right? It's pretty. But you can do much better now that we have lambdas. Instead of actually overriding these things, we can simply pass in lambdas. So instead of having constant-specific class bodies, we can simply have constant-specific fields, which is a much simpler, clearer idiom. So in this case, each of the types, it takes its symbol, like plus for plus, and then a lambda to describe what it ought to do. And the actual implementation of apply is the same for all of them. It simply takes the op, which is this function object that we're passing in and storing in the constructor, and it applies it to the 2 arguments. So I hope you'll all agree that that's a lot prettier. And that is just one instance of the sort of thing that is practical with lambdas that wasn't practical with anonymous classes. It's not that you could not have done this with anonymous classes, it's that it would have looked too awful to actually do. So that's the best thing about lambdas. They make a whole class of sort of object-oriented idioms that would have been too ugly to use. They make them pretty in Java. So, caveats. First of all, lambdas lack names and documentations. They are anonymous little blobs of code, and if the reader of your program cannot, by inspection, know what the lambda does, then you shouldn't be using a lambda. If it exceeds a line or 2, you shouldn't be using a lambda. So what do you do? What do you use instead? And what you typically do is extract that code out into a method and then pass a method reference to that method. Or for an enum, you can use an instance-specific class body. Those work even if they don't fit into a line or 2. And by the way, even in the era of lambdas, anonymous classes still do have a few uses. You can only use lambdas where you have a functional interface, which means it has only one abstract method. If it's got more, then you need to use an anonymous class. And then a slightly obscure one, but it is important. Lambdas cannot refer to themselves. If you have the keyword this inside a lambda, it refers to the enclosing object. And that's usually what you want, but it isn't always what you want. In particular, if you're passing a callback, say in a GUI application, which has to deschedule itself. When it decides it no longer needs to run, it has to say, hey, take me off the list of callbacks. You can only do that if it can refer to itself, and it can only refer to itself if it's an anonymous class instance. So basically, anonymous classes are rarely useful, but they are still useful in the era of lambdas. All right, part 2, prefer method references to lambdas. Method references, as I'm sure you all know, are little function objects that simply refer to pre-existing functions. So simple example here, well, somewhat simple, I suppose, is if we merge a map, using map.merge here, we can pass, sort of using a lambda, we can say, hey, given the existing count associated with this key and an increment, replace it by the count plus the increment, and the increment is 1. So basically, add 1 to the count for this key. And this, by the way, this little simple operation will basically get you a frequency table. So it's nice and it's powerful, but you can do even better using method references. Instead of having this little lambda here, if you just say integer : sum, that's a reference to a pre-existing method called sum on the integer class. And I would say that's arguably easier to read. You know, merge this map using sum on the values associated with each key and adding 1 to the value associated with each key. That wasn't, I didn't say precisely what that did, but I'm going to move on anyway, just because I'm short of time. You know, ask me afterwards if you want to know what this really does. Anyway, the more parameters you have, the bigger the win for using method references instead of lambdas, because a lambda, you actually explicitly have every parameter mentioned, whereas method references don't mention any of the parameters. So if you've got a lot of parameters, the method reference is a lot shorter, but the parameters are sometimes good. If you choose the names carefully for the parameters, they can actually tell you something about what you're doing with them. In this case, they don't really pay for themselves, but it does tell you that the first thing that's being passed in is the count currently associated with this key. That's the old value associated with the key. And the next one is 1, which is an increment, and it returns the count plus the increment, basically adding 1 to the count. So occasionally, lambdas are better than method references. When is this true? Well, for instance, it's true if all you're doing is passing a reference to a static method in your own class. Here's how the lambda looks. Takes nothing and returns a call to action. Whereas if you have to do it using a method reference and the class has a really long name, like, gosh, this class name is humongous, well, you end up with this really long and pretty ugly method reference. And moreover, it's more confusing because if you forget what class you're in, seeing this long class name doesn't tell you it's the same class, whereas seeing it without a class name does strongly indicate that it probably is. Lambdas similarly can beat function factories. There's something in function called function.identity that returns the identity function of an appropriate type. And when people see it, they say, ooh, and they use it every time they can. But it turns out that it's really kind of longer and uglier than simply saying, you know, a function that takes x and returns x. So you should generally, oh, right. Another thing is there are 5 different kinds of method references. Everything that I've shown you so far in this talk is simply a static method reference. So, you know, integer : parseInt refers to the static method parseInt in integer. And the lambda equivalent is, you know, take a parameter and call integer.parseInt on that parameter. Those are great as far as they go. Another nice kind, and the point of this slide is you should know and use all 5 kinds of method references. How many people knew there were 5 kinds of method references? Yeah, a smattering of you. Anyway, so bound method references are great. Basically, you specify an object reference at the time that you create the lambda, and then the parameters on the named method on that object are the parameters to the lambda. And you can actually use the object reference to perform a little bit of code that's captured at the time that you create the lambda. So here's a nice example of that. If I call instant.now, : isAfter, well, it calls the isAfter method on an object representing the time at which the lambda was instantiated. So basically, it's a predicate that returns true for every time that is after the current time. And it's kind of nice that you can do something that powerful with this little code. If you did the same thing with lambdas, you would have to say instant then equals the current instant, and then the lambda would be t as an input parameter, and then is after t as the result of the lambda. So I think we can all agree that this is a lot nicer than this. Then you have unbound method references, which are references to instance methods where the object to which the thing is going to be applied is added as the initial parameter to the lambda. So it's got n plus 1 parameters if the method has n parameters. And finally, we have class and array constructors. Those are just like static methods, except that you use them when you want to create instances of a class or an array. So they're a nice way to get little factory objects that you can pass around to create instances of classes and arrays. So know them and use them, all 5. And the bottom line is that almost anything that you can do with a method reference, you can also do with a lambda. Method references don't make it possible to do anything new, but they usually make it a little bit more succinct, a little bit clearer, a little bit shorter to do the same thing. So if they work for you, use them, but sometimes lambdas are clearer. Use your best judgment, and if you got it wrong, no problem, because this is just an implementation detail. You can change it after the fact. It isn't like screwing up an interface. All right, third part of the talk, 3 out of 5, favor the standard functional interfaces. And I'm going to kind of motivate this with a little example. So before we had lambdas, the template method pattern from the Gang of 4 Patterns book was a fairly common way of doing things, where if you had a class whose behavior was parameterized on one function, or one or more functions, the way you did it was you took the class and you extended it, and you overrode the functions that would change the behaviors. And a classic example of that, which I wrote, is linked hash map, where there is a method in the base class called remove eldest entry. And the implementation in the base class simply returns false, so it never removes the eldest entry. But this is invoked automatically, a callback, if you will, every time you add something to the map. And it gives you the opportunity to remove the oldest entry from the map if a certain condition is true. What condition? Well, anything you like, whatever you put in the code for this remove eldest entry method. So in this case, it returns true if the current size of the map is greater than some maximum size, let's say 100. And what you get from that is, of course, an LRU, or least recently used cache, where once the map gets its 101st element added, the oldest one is automatically deleted, and it remains with exactly 100 entries, no matter how many entries are added to the map. So that's nice, but it's a little nasty to have to extend a class, to write a whole new class, just to parameterize its behavior in that fashion. So in the era of lambdas, you're much better off. And by the way, this is fiction here. There is no constructor like this. We sort of already went down the other route. But there could be a constructor on linked hash map that takes an eldest entry removal function that sort of specifies this policy, rather than having to extend the class in order to specify the policy by overriding a method. And what would this eldest entry removal function actually look like? It would have one method called remove, and it would be a Boolean method that returned true if the element should be removed. And as far as parameters, it would get the map itself and the entry that is optionally to be removed. And then you would make the cache, instead of by extending the class, simply by creating a new linked hash map, and you'd pass in a lambda that takes the map and the eldest entry and returns some function of the two. In this case, map.size greater than max size. So this is the same functionality as the example above it. And the problem with this code is it has this sort of silly eldest entry removal function type. And we don't need that type. Instead, we can use one of the standard functional interfaces. Here are the standard functional interfaces. And sadly, there are 43 of them. How can you remember 43 interfaces? It's kind of nasty. But the nice thing is that there is some structure to them. So if you can remember these 6, it turns out that you can sort of derive the other. And in the book, in this 3rd edition of Effective Java, I have sort of a few pages which I claim, if you read them, you'll be able to sort of have a mental map of all 43 of those interfaces. A unary operator is simply something that takes an object of type T and returns another object of type T. Binary operator takes 2 objects of T, returns a T. A predicate takes 1 object of type T and returns either true or false. You saw an example of a predicate. And then a function has 2 types, and it takes an object of type T, returns an object of type R. A supplier takes no argument and generates T. So it's kind of like a factory object for T's. And a consumer takes objects of type T and returns nothing. So it's just a sink for T's. And the consumer is used, let's say, as the body of a for loop, where it takes all of the successive instances of some value of type T and applies some process to them. And most of the remaining 37 interfaces do the same things, but they do them to the primitive types, or at least to 3 of the primitive types, ints, longs, and doubles. And you could not bother using them. You could always use the function objects, but do so at, you could always use the object reference variants, but do so at your own peril. If you do that, you'll be doing lots of auto-boxing and auto-unboxing. Why is that a bad idea? Oh, come on, shout it out. One word. Performance, good. We have one brave person in the audience, and she is over there. All right, so the advantages of using the standard functional interfaces instead of rolling your own, as we did in the example on the first slide with the eldest entry removal function, are that you're using a standard interface that everyone already knows, so you reduce the conceptual surface area of your API. In order to learn to use this new API, you don't have to learn all of its little functional interfaces. You just use the functional interfaces that everyone already knows and perhaps loves. Also, you get interoperability benefits because you're using the same interfaces that other people are using. So if you want, a predicate on input, well, there are lots of libraries of predicates. You can use pre-existing predicates. And moreover, you can take multiple predicates and combine them using these default methods that were added to the predicate interface. So you can take an arbitrary collection of predicates, and you can do arbitrary Boolean expressions. You can basically say a predicate that consists of this predicate and this predicate, or that predicate, using the and or methods that were added to predicate. So generally speaking, by using these pre-existing types, you provide great interoperability and power benefits to your users. In our linked hash map example, instead of using remove eldest entry function, whatever I called it, it's just a by predicate from map of kv and map.entry of kb. What is a by predicate? It's a binary predicate, a predicate that takes 2 values instead of 1, and they can have different types. So in this case, I get a map on input, I get a map entry of the same type on input, and I return true or false, because it's a predicate. So this is clearly the correct type to use in our cache example. So now you know when you should use these standard functional interfaces instead of rolling your own. But when should you make your own functional interfaces? Well, of course you have to do it if none of the standard ones apply, right? There are only 37 of them, and 37 is a lot, but there are more than 37 possible functional interfaces. So if you're using something that simply doesn't fit into one of those categories, then you've got to roll your own. But now let's consider the case of comparator. Comparator is, in fact, structurally identical to a 2int bifunction of t comma t. Does that mean that they should have used that instead of comparator if it had existed back then? It certainly doesn't feel right. I would say the answer is definitely not. But why not? What's so special about comparator? First of all, it's got a nice name. It's a comparator. You use it to compare things. That provides useful information. Every time an API calls for a comparator, you know, aha, it's getting something that specifies an ordering on objects. So it tells you something nice about the API. And not only that, but there are strong requirements on valid instances of comparators. In order to be a comparator, you have to be transitive and anti-symmetric and reflexive. There are certain properties that you have. They are the so-called general contract of the comparator type, and you can read about it in the Java doc for comparator. And by implementing a comparator, you pledge to adhere to that. So if anybody gets a comparator, they know that it actually does impose a total ordering, because it would be illegal to call it a comparator if it didn't do that. And no one would ever do such a thing, right? At least not intentionally. Finally, many useful default methods can be added to some of these interfaces. And let's take a look at comparator. It has those sort of comparator combiners that I was talking about before. Some people call them combinators. That's kind of just a fancy word for function object factories, but something that takes two comparators and returns a it takes multiple comparators and returns a comparator that effectively applies them in sequence so that you can get a comparator that gives you the lexicographic ordering where you say, well, all right, try the primary key, and if the primary keys are equal, try a secondary one, and if that's equal, try a tertiary one, and go on as long as you like. You can do this kind of thing only if you make your own custom interface. It wouldn't make sense to sort of add methods like that to the standard functional interface because they have to sort of be all things to all people. So that's what's so special about comparator, and that provides a set of criteria for when you should roll your own functional interfaces. You should do it, first of all, if your interface has a decent name, a good descriptive name, and is likely to be commonly used. If it's only going to be used rarely, then the name perhaps doesn't matter so much. If it's going to basically propagate to a whole bunch of other interfaces, as comparator did, and there's a nice name for it, like comparator, and if it has a strong contract associated with it, like the general contract for comparators, and finally, if it would benefit from default methods. You don't need all four of these criteria, but if a number of these criteria apply, then your interface is a good candidate for being a custom functional interface, even if one of the standard ones would apply. So just think about these four things every time you're deciding whether to use one of the pre-existing functional interfaces or roll your own. But if you do decide to roll your own, this is critical. If you write a functional interface, remember, it is an interface. Interfaces are forever. Interfaces should be designed very, very carefully. In fact, there's a whole item about that in effective Java, and I believe it to be even truer than it used to be, even in the era of default methods. Define interfaces as if your life depended on it, because not only does your life depend on it, but the lives of everyone who has to use your interface and everyone who has to use the software that is built upon your interface. End of sermon. So, part 4, use streams judiciously. So streams are a new processing model that was added to Java 8, and the stream is, it's not all that complex, and this slide is probably a review for most of you. Hang on. So, what is a stream? Well, it's just a bunch of data objects from, say, a collection or an array or an input device or random numbers or something else to be processed in bulk. That's all it is. It's processed by a pipeline, and all pipelines consist of exactly one stream generator that is the source of the data, 0 or more intermediate stream operations, things that process the data, and then one terminal stream operation, which takes all the elements of the stream and does something to them, like puts them into a collection or prints them out or some such. It supports mostly functional data processing, and it enables painless parallelism. You can make a stream run in parallel instead of serially simply by adding a call to the method invocation parallel stream, which is really nice. You may or you may not see a performance improvement, and I hope I have time to get to the last part of the talk, which is about whether you do or don't. So here's a nice little example, and if you understand this example, then you basically understand streams. This prints out the first 20 Mersenne primes, and as a reminder to you, a Mersenne prime is a Mersenne number that happens to be prime, and a Mersenne number is a number of the form 2 to the p minus 1, where p itself must be prime. So take a prime, let's say 3. 2 to the 3 is 8, minus 1 is 7. Is 7 a prime? Yes, it is. So 7 is a Mersenne prime. So here's a little program that prints out the first 20 Mersenne primes. And its data source is a stream of all of the primes, which we've called primes. This method returns a stream of all the primes. And if you are new to streams, you might say, all the primes, how can you do that? There are infinitely many primes. And the answer is because streams are evaluated lazily they can have infinite size. You won't necessarily process every element on them, but if you keep calling them, you keep getting more primes. So how does this look? It uses the stream.iterate method, which returns a stream whose first element is the one I pass in here. The first element is 2. And by the way, this is actually big integer.2. I assume we've done a static import of all the elements of big integer, just so this fits on a line of a slide. So we start with 2, and then to compute the next prime from the last one, I call big integer.next probable prime on it. So if I call next probable prime of 2, what do I get? 3. And if I call 3, I get 5, and so on and so forth. So this generates not all the Mersenne primes, but all the primes. Now, how do I get all the Mersenne primes? Well, I take all the primes, then I map each prime to 2 to the power of that prime, and I subtract 1 from it. So, the first thing I'm passing in is 2. 2 to the 2 is 4. Minus 1 is 3. And then I filter it. How do I filter it? I filter it using the predicate that takes the Mersenne number. And notice how I've chosen the name of the parameter carefully, as I told you to do that before. So I call the parameter Mersenne because it's a Mersenne number, and I return Mersenne.isProbablePrime of 50. Sorry about the 50. It's a magic number, and once again, I did it to make it fit on a slide. And I'm sorry also that I designed this API that requires you to pass in a magic number. It's like the number of steps in the Miller-Rabin algorithm. You don't care, but basically just take my word for it. If you pass in 50, it's not going to lie to you. It will return true if it is a prime and false if it isn't. So this is simply a predicate that could be called is probably prime and doesn't take any argument. And then .limit 20 just says, give me the first 20 of these Mersenne primes. Don't give me all of them, because there are infinitely many, but lazily evaluate that stream and stop when you get to the 20th one. And then finally, the terminal operation of this stream pipeline, it says for each of these 20 Mersenne primes, call the method reference system.out::println, a static method reference, on each one. So right here, we have an entire complete runnable program to print the first 20 Mersenne primes. So pretty cool, right? Nice demonstration of the power of streams. Here is an iterative program, so no lambdas here, to compute all the anagram groups in a dictionary. And do you all know what an anagram group is? I'm going to actually run through this quickly in hopes of getting to the third one. But an anagram group is a bunch of words that have the same letters in different arrangements. So for English words, the words stop, pots, opt, tops, they all have the same letters, T-O-P-S. And this program actually takes an entire dictionary file and prints all of the anagram groups greater than some minimum size. And I'm not cheating. This will actually run. This is the whole program. And moreover, it's actually pretty easy to understand. I'll try to go over it here in under 30 seconds. So we open a file, or we create a file whose name is the first argument, a string. The minimum group size, we parse the second argument, which should be an integer. And then we create a map from a string to a set of strings, and that map will contain the anagram groups. The keys for this map are going to be the words alphabetized, because if you take anagrams like stop and pots, and you actually alphabetize the letters, that is, put the first letter first, all anagrams will have the same alphabetized form. So that's just a way to sort of bring all of the words together into a single bucket, not single bucket, but single entry of the map. So basically, we try creating a scanner over the entire dictionary. And while the scanner has more, while there are more words in the dictionary, we say a word equals the next element of the scanner. And then we call compute if absent, which is a method that was added in Java 8. It's a great method. It was actually added to initially to the parallel maps, Doug Lee's concurrent hash map, and then it was added using default methods to the map API because it's so useful. And basically, the key here is calling the alphabetized method on word, and the way you compute the value of the thing is if it's absent, then you take a new tree set. Otherwise, you take the tree set that was already there, and you add the new word to the tree set. So basically, if you just run through the map doing this, you'll end up with each entry being a map from the alphagram, the alphabetized word, to all of its anagrams, right? And then finally, we iterate over all of the values in this map. The values are basically word, set of words, pairs, and if the size of the anagram group is greater than the minimum group size, we print it out. So hopefully you understood that. I apologize if you didn't. I'm just running short on time. But this program really will print out all of the anagram groups in a dictionary whose size is greater than some minimum size. And the reason I did this is because otherwise, it'll just print too many groups, too much garbage. You won't want to read it all. And you need this helper function, which alphabetizes a word. It just takes the word, turns it into an array of characters, sorts those alphabetically, arrays.sort A, and finally it returns a string whose characters are the characters in the now sorted array. That makes sense to everybody? Good. Now, suppose we want to do this with streams. Looks like it should work pretty well with streams, right? Here's what you get. I'm not going to go over this because it's unreadable slop. This is overuse of streams. If you just take streams and say, ooh, everything here feels like a stream, I'm going to do it all as one giant stream pipeline, this is what you get. And I guarantee you, I was not trying to make it ugly. I just basically said, I'm going to use streams to the maximum extent that I can. This is what I ended up with. I don't like it. Does it mean I shouldn't use streams for this? Not at all. It means I should use streams tastefully. Here's how to use them tastefully. So, here we get the dictionary, we get the group size just as we did before, and now we do it. Notice, by the way, that I'm using the try finally here so that the file will automatically get closed, even if you exit the thing abnormally by throwing an error message. But anyway, so I get a stream of all of the words in the dictionary by calling files.lines, which is a wonderful thing that was added in Java 7, I guess. 7 is right for files? Yeah. Anyway, and then what do? Well, I call the collect method on this stream, which basically does the same trick I was doing with the map before. It takes the elements of the stream and it collects ones that kind of agree grouping by word maps to alphabetized words. So all of the words that map to the same word will be collected, and I'll end up with, and by the way, that's a terminal operation, I will end up with a map from alphagram to set of anagrams, and then I'll stream that thing. So now I'm streaming through these sets of anagrams, and I'll filter those where I only let ones go by if the group size is greater than or equal to the minimum group size, and for each element in a group, and by the way, this should say group rather than G, but I didn't have space on the slide, so I violated my own rule about picking your parameter names nicely. So for every group, print out the size and the group. And don't you think this is nicer than either of the previous programs? It's nicer than the purely iterative solution or the too streamy solution. So this is basically the happy medium, and it combines iterations and streaming. And there's a lesson there. Good programs tend to combine iterations and streamings. And by the way, you may notice that I did not use streams to implement alphabetize. Why not? Well, the reason is that streams don't offer direct support for char, and if I tried to sort of force the square peg into the round hole, the resulting implementation would have been difficult to read, difficult to write correctly, and probably slower. And if you don't believe me, here's a little puzzler for you. So here we have a program. The string hello world we call .chars, which gives you a stream of the characters in the string. And then for each of the characters, we call system.out print on the character. So what does it print? Yell out the answer. Wow. So you all got it. You're experienced. It prints exactly this garbage. And the reason it prints this garbage, as you know, is because the chars method on Hello World returns not a stream of characters, but a stream of integers, because it's more efficient to use a primitive type, but there is no stream over the chars, so it uses a stream of int rather than a stream of character. And so when you call printf, you're getting the version that takes an int and it prints the integer, and it's kind of ugly. I would say, by the way, the real fault in this puzzler is in this chars method. That should be in red. It's really unfriendly to call a method chars if it returns ints, don't you think? I mean, That's confusing. Anyway, so that's the problem, and the way you can correct it is if you cast the int to a char, then it will print out hello world. The moral is that streams only work for object reference types, ints, longs, and doubles. If you want to use something else, be careful. Don't use streams for character processing. A quick conundrum: which of these two is better? These things are computing the Cartesian product. This one, they both basically give you a whole deck of cards, playing cards, with all of the suits, spades, hearts, diamonds, clubs, and all of the ranks, from ace, deuce, whatever. So this is the code that you're probably used to. It's just a nested for loop where you go over all of the suits, over all of the ranks, and you add to a result a new card, which has the given suit and rank, and you return the result. Here's a version that works using streams. It's a little more complicated. It uses currying. It has a nested lambda, and it uses the flat map construct. I'm not going to go into it in detail. And I honestly don't know which of these two is better. I think which is better is a function of who you're working with, what they're comfortable with. I'm curious, by show of hands, how many people think the first version is better, the traditional version? About 75% of you. So how many people think the second one is better? Yeah, about 25. And I think that's perfectly reasonable. You're all right, and you should all feel good about your answer. All right, so bottom line, streams are great for many things, but they're not a panacea. So when you first learn them, you have this temptation to say, oh, everything's a stream, I'll do it all with streams. Don't, because it'll make your code uglier and harder to maintain. Exercise judgment. Use them when you should, and it isn't always clear at the outset whether you should use streams or not, so try it. If it works well with streams, great, and if not, try again. So now I'm going to try and very quickly go over this because it's cute. Here's our Mersenne primes program. Remember it? On my machine, it takes 12.5 seconds to run and generate all 20 of these Mersenne primes. That's kind of great. Suppose that I simply add the dot parallel. About how long do you think it would take to run? Yell it out. I'm curious what your feeling is. Same time, so it's not going to make it any faster. All right, so it turns out it runs very, very slowly. I let it run for half an hour. My room got noticeably hotter. I could hear the fan on my machine running, and it had not printed a single prime. I terminated the program. What's going on? Why is it running so damn slowly? Well, Streams library has no idea how to parallelize this thing, and the heuristics fail miserably. Even in the best case, parallel is unlikely to help you if either the source is made by stream.iterate, it is, or a limit operation is used, it is. So this does two things that don't work well with parallelism, and it isn't the best case. The problem is the default strategy for limit computes extra elements and then it says, oh, there are too many, we'll throw some away. Problem with Mersenne prime calculation is computing each one takes as long as computing all of its predecessors, right? So it's exponentially slow in the number of Mersenne primes you compute. So if you compute 5 extra, you're quite hosed. It's, whatever it is, 32 times slower. So the moral is do not parallelize indiscriminately. Parallelism is an optimization. Treat it like any other optimization. Test before and after under realistic conditions, and only if it really does make your program faster should you use it. The book tells you a lot about when it will make your program faster, and this is the happy ending. Here's another program that computes the number of primes less than n, called pi of n. And it's pretty straightforward as well. We take a long stream from 2 to n. We map each object to a big integer, and we filter by is it a prime or not. Once again, 50, the magic number. And finally, we count how many primes there are. It takes 31 seconds to count how many primes there are between 2 and 10 to the 8th on my machine. So how fast does this one run if I add dot parallel? 9.2 seconds, which is 3.7 times as faster on a 4-processor machine. So that's the best we could hope for, and it's doing it with no additional work on my part. So under the right circumstances, dot parallel is wonderful, but it's actually rarely wonderful, so be careful. It's merely an optimization. And in conclusion, Java is larger and more complex than it once was. It is a multi-paradigm language, and now you have to not just know how to use the features, but which feature to use. Lambdas and streams can be a big win, but use them judiciously with great power, comes great responsibility. I am happy to answer all your questions, and you should buy a copy of this wonderful book. This is what we call in English a shameless plug. And these are promo codes that will get it for you cheap on Informate. And I also have these free bookmarks, which I will sign for you and give you if you want. I'll hang out as long as you like and answer your questions. Thank you very much, and enjoy the rest of Devoxx France.